How do thermodynamic cycles work in practical engines? Have you ever wondered how engines transform heat into the power that drives our vehicles? Understanding thermodynamic cycles is key to this process. Let's break it down in a simple way. Thermodynamic cycles are essential for engines to convert heat energy into mechanical work. These cycles involve a working fluid, which can be air, a fuel-air mixture, or steam. The fluid goes through changes in pressure, volume, and temperature. It absorbs heat from a high-temperature source and releases some heat to a low-temperature sink while producing useful work. At the heart of thermodynamic cycles is a repeating sequence of processes that return the working fluid to its original state. This repetition allows engines to operate continuously, generating power over time. Different types of engines use various thermodynamic cycles based on their design and fuel type. For internal combustion engines, the Otto cycle is commonly used in gasoline engines. This cycle has four main stages. First, the air-fuel mixture is compressed without heat exchange. Next, combustion occurs at constant volume, where heat is quickly added by burning fuel. Then comes the expansion phase, where hot gases push the piston, again without heat exchange. Finally, the exhaust phase occurs at constant volume, where heat is rejected. The efficiency of this cycle depends on the compression ratio. Higher compression leads to more efficient energy conversion. In diesel engines, the diesel cycle is used. This cycle differs by adding heat at constant pressure instead of constant volume. Diesel engines ignite fuel through compression heating rather than using a spark. External combustion engines often use the Rankine cycle, which is common in steam turbines and power plants. In this cycle, water is heated to produce steam. The steam expands through a turbine to generate work and is then condensed back to liquid to repeat the cycle. Another external combustion cycle is the Stirling cycle. This cycle uses a fixed amount of gas inside the engine, which is alternately heated and cooled externally. It is known for its high efficiency and ability to use various heat sources, including solar energy or combustion. Gas turbines operate using the Brayton cycle. In this cycle, air is compressed and then heated at constant pressure by burning fuel. The heated air expands through a turbine to produce work. In all these cycles, the main principle is transferring heat into the working fluid at high temperatures and rejecting heat at lower temperatures. The difference in heat is converted into mechanical work. The working fluid undergoes compression and expansion, allowing the cycle to repeat continuously, keeping the engine running. Real-world engines differ from ideal cycles due to factors like friction, heat losses, and incomplete combustion, which can reduce efficiency. However, understanding thermodynamic cycles helps engineers design engines that maximize work output while minimizing fuel consumption and emissions. Thermodynamic cycles guide the sequence of heating, expansion, cooling, and compression of a working fluid. This process enables the conversion of heat energy into mechanical energy in a controlled manner. With this knowledge, we can appreciate how everyday engines power our vehicles, power plants, and machinery.